Stop rerunning duplicate LLM jobs forever. By the end, you will build a simple idempotent job layer in Python, dedupe repeated prompts, and resume work without redoing finished items. You will see a small deterministic LLM stand-in and a clear pattern you can plug into workers or pipelines. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Real pipelines submit many similar prompts. A single mistake or crash can cause the same prompt to run 10 times. That wastes tokens, time, and money. Success here means each unique user intent runs once, duplicates collapse, and interrupted work picks up where it left off. Compared to brute force retries, idempotent jobs give predictable cost and easy auditability, though you trade some recall for stricter deduplication if you normalize aggressively. The core idea is simple. Turn a prompt into a stable job key. Use that key to skip work you already did. Optionally normalize the text so near duplicates count as the same job. Imagine a short list of prompts where 2 lines are the same question typed slightly differently. We want 1 result, not 3. We will build a tiny pipeline that hashes prompts, runs a deterministic mock LLM, removes duplicates, prioritizes by cost, normalizes near duplicates, and finally resumes with a cache. That is what you will see executed next. This snippet shows the minimal idempotent idea. It hashes prompts to produce a job key, and then runs a deterministic mock LLM that uppercases text so output is predictable. The list of prompts deliberately includes duplicates to demonstrate deduplication. The function key computes an 8-character SHA-1 digest, which is a fixed-length fingerprint of the text, and we use that digest to identify jobs. The dictionary unique keeps 1 prompt per key and preserves the latest occurrence, removing exact duplicates. We then sort outputs so ordering is stable across runs. The printed list shows the first 2 unique results that would be executed, demonstrating basic dedupe and deterministic execution. Next, we will show how to avoid redoing finished work and resume a run cleanly. This example demonstrates resume behavior by skipping keys that are already marked as done. A set called done holds the job keys completed in earlier runs, which acts as the resume anchor. We rebuild the dictionary penned by keeping only items whose key is not in done, so both duplicates and finished items are filtered out at once. Then we apply the same deterministic mock LLM to each remaining prompt. Sorting again ensures stable presentation. The printed list shows exactly which prompts would run now, confirming that any previously completed work is not repeated, and that the pipeline can pick up where it left off. Next, we will prioritize work by cost, so expensive jobs run first. This code prioritizes pending jobs by an estimated token cost and schedules the longest first. We keep the done set as our resume reference and rebuild penned from the incoming prompts. The list plan is computed by sorting penned values with a key that prefers longer strings, which is a simple proxy for token cost, and uses the text itself to break ties deterministically. Picking only the first 2 items demonstrates a clear scheduling decision you could feed to a worker pool or a set of parallel workers. The printed plan shows the order you would process next, letting you control latency or throughput by selecting more or fewer top items. Next, we will normalize text to collapse near duplicates before hashing. This snippet adds canonicalization to the pipeline so near duplicates map together before we compute keys. The variable ag toggles aggressive normalization. The function norm lower cases and collapses extra white space, so prompts like write haiku and write haiku become the same canonical form. We feed that canonical form into the key function and also record it in unique, so the recorded task reflects what actually gets sent. If you set ag to false, fewer strings collapse together. which means you would process more jobs and spend more tokens, but keep higher recall. The printed list shows the canonical unique tasks after stronger deduplication and makes the trade-off concrete. Next, we will combine normalization, resume, and memoization into a single idempotent baseline. This code combines the ideas into an idempotent baseline that normalizes text, resumes from finished keys, and memoizes results to avoid repeated work. The function key here reuses the normalized text as the job identifier, so identical canonical prompts map directly to the same cache entry. The dictionary cache is preceded with a completed summarized doc result to simulate a previous run and to show how new tasks are appended. We construct a new mapping by keeping only unseen keys, compute outputs deterministically for those, and update the cache. The small summary output reports how many tasks were processed in this run and the total accumulated unique results. The printed dictionary verifies idempotent behavior and a clean resume. Recap: 1. Idempotent LLM jobs use a stable key to ensure each intent runs once. 2. Combine resume sets and memoization to avoid redoing work across crashes or restarts. 3. Normalize carefully. Aggressive canonicalization reduces cost, but can collapse distinct intents, so tune it. Next step, tune the normalization aggression parameter and measure the trade-off between unique outputs and token cost on a larger corpus to find the sweet spot for your workload. If practical AI engineering helps, subscribe and watch the AI engineering videos.